Good afternoon, everyone. Once again, we are very happy to continue with our lectures on particle physics. Currently, sir is giving an overview. So, yesterday he began with a very uh, detailed introduction regarding the physics from before 1900, and then is almost covered till what has happened till standard model. And today, sir will be continuing with his lecture. Today it's titled Thrilling Search of Fundamental Particles of Matter. Over to sir.
Thanks, Shastriji. So let me continue with this. Good afternoon, everybody. So welcome to this second session. And as I mentioned that yesterday we learned about a little bit of prehistory and what was the situation of physics before 1900 and how things changed after 900. So the outline is continuing. So today we will focus how high energy physics, the subject of high energy physics was developed. And then formally we will go to classification of elementary particles. And very important concept is the internal symmetries, how we are going to use them. And of course, we may continue tomorrow or maybe other day to go for fundamental forces if we couldn't complete it today. So just as a quick reminder, what we did yesterday was before 1900, all the matter was supposed to be in three, four forms: solid, liquid, gas, plasma. And all variety of matter was basically a mixture of compounds, elements. Compounds were themselves made up of elements, and there are around 108 or 104 elements, and there are millions of organic compounds and hundred thousands of uh, inorganic compounds, molecules made up of around 100 atoms. This is what we learned finally through our chemist friends. Particularly, Dalton gave very big score to the atomic structure. And as far as forces were concerned, only two forces were known: gravity and electromagnetic. Quite understandably, because both of them have infinite range, whereas in contrast to recently uh, observed forces, strong forces and weak have very short range. So we'll come to that later. But we understood gravity through Newton's laws, and which is a universal law, range having infinity. But the good thing is, through that, Newton unified terrestrial gravity and celestial gravity. Why I am emphasizing it? Because unification is a very important theme of high energy physics. So sometimes people ask that unification occur only recently. So I want to tell them that no, unification has been started right from the time of Newton. On one hand, he also showed that terrestrial gravity and celestial gravity are basically the same gravity, and formula is the same. Besides that, we also learned that all other forces apparently which we are seeing, like muscle forces, electric forces, magnetic forces, and all other kind of friction also, all those are essentially electromagnetic. In fact, life too. And that electromagnetic force again had infinite range. And Faraday gave the idea of classical field as a propagator of force from one charged particle to another. Same idea can also be applied to gravity. Every massive object is surrounded by gravitational field, which in turn affect other massive objects. However, formal classical field theory of electromagnetism was developed by Maxwell around 1860, though it was based upon lots of the work done by Coulomb, Ampere, Biot-Savart, Faraday, and many others. So the another thing is this also was one of the first ones unified electricity and magnetism. So we have in electromagnetism a unification of electric and magnetic forces, and whenever we unify two things, we always end up with more than the two. And here the bonus was optics. So the whole of optics could be understood in terms of Maxwell equations. So this was the situation around 1900 or before that. And then after 1900, as I mentioned yesterday, philosophical marvel took place. We have more and more understanding of structure of matter and its interaction. This has been really a work of great beauty and symmetry. Major revolutions took place were developed by Einstein to give us special theory of relativity and general theory of relativity. Those theories presented unified picture of space time and also of matter in a way. And then quantum theory was another very important revolution, which was developed in three stages. First stage is pre-quantum mechanics, elementary ideas which we hear about, duality principle, correspondence principle, uncertainty principles, and of course the basic thing is quantization, that everything cannot have anything value, every actual real value. They have to have discrete value. So that was a new concept which was foreign to the classical mechanics. So initial efforts were made by Planck, Einstein, Bohr, probably all of you probably know, and maybe I will touch these things in more detail in the lectures of quantum mechanics formally. And then formal quantum mechanics was developed around 1920, 27, 30, when first form was developed by Heisenberg as a matrix mechanics. Within 2 years, Schrödinger developed wave mechanics. And then, of course, the proper interpretation of the wave function and Pauli ideas of spin, and then the synthesis of quantum mechanics with the relativity, the great work of the Dirac, which predicted antiparticles. But finally, whenever we learn more, we end up with having more and more questions. So proper picture could be obtained only in quantum field theoretical development. We have a quantum field theory of electromagnetism interaction, which was developed finally by Feynman, Schwenger, Kamanaga around 1948, just after the World War II. It involves the use of creation, destruction operator. So the whole world picture was changed. In fact, this question, what is a force, is still puzzling. I will again elaborate this more on in some other time. But still, I will throw this question to you. Do you really understand what is a force? How many ways we can think of the force? We can think of force as a formula. We can think of force acting through some field. We can also think of force acting through exchange of certain quanta. And in general theory of relativity, we find there is nothing like force, just a curvature of space-time. So still, we really understand force is a very important question. However, in this development, not only in quantum theorem physics, but also in classical physics, people found the relevance and importance of symmetries, which are broadly discrete and continuous. And a formal mathematical framework required to describe symmetry is the group theory. Why I'm reminding this thing is because in high energy physics, we are going to use later on at the end non-Abelian relativistic quantum field theories. So we need quantum mechanics, we need to know quantum fields, we need to know symmetries, and we also, of course, need to know relativity. So that is why these are going to be the basic mathematical apparatus on which particle physics, high energy physics has finally standing on. So I must not forget that the great works of high energy physics, the great, results of high energy physics could not be obtained without him. The work is a big teamwork of 20th century, which is still continuing. And it started with cosmic ray studies and simple Rutherford scattering experiments and all that. And we all know cyclotron, various kinds of accelerators which are providing higher energy. And then how to use detectors to study the outcome of various scattering and collision experiments. Lab frame, they may be done in center of mass frame. So in those accelerator experiments, observation and creation of new kinds of matter has been done. That matter unstable as well as stable. The stable matter we see around, but unstable matter is created, and that starts decaying as soon as it is produced with a very small lifetime. So starting with ordinary microscope, which help you to see the structure, we have gone to large hadron collider. Size of the Excel, this biggest microscope is around 27-kilometer ring lying between under the ground of two countries, France and Switzerland. Maybe in some of the talks I can talk more about large hadron collider. So the basic spirit of all these collision experiments or scattering experiments is to exploit available kinetic energy to create new forms of matter which are not usually seen. So what is happening is, suppose we take hadron collision. In center of mass experiments, the whole of the kinetic energy of the two particle and sometimes even mass, because if antiparticle are they are colliding with particles, they both will be annihilated, and the whole thing will be just nothing but large amount of energy, which can be which converts itself into new form of particle. That is how we see lots of new particles, which will learn. So once we have this unstable massive particle, they start decaying. So we have to have very fast detection techniques. Earlier, we all have heard about Wilson cloud chamber, bubble chambers. Later on, pictures were taken of the phenomena and they were studied manually. But now the processes are going so fast at very high energy. We have to have automatic detections. So multi-layer detectors have been made, and the observation of measurement of all the things are left to the computers. So very advanced form of detectors and very advanced level of computers hardware as well as software side has been used. In fact, even before experiment is taken out, is actually performed, people have simulators to know what kind of events can occur. So it has become a very formal science. So on this side, I have to admire the great efforts put by experimentalists friends, and this interplay between theory and experiment led to the so-called standard model, which we have today, standard model of high energy physics, standard model of elementary particles and fundamental forces. And of course, I will give a caution here that it's not end of the story. There are new questions which are coming from standard model and which will be answered probably in future. So we are slowly moving towards the standard model. So let me now come to the today's part. So see our own this main theme of question is to give you overview of elementary particles which we find constituting matter. And of course, complementary talk will also come where we will study in more detail how the forces among these fundamental particles take place. However, just to remind you, somewhere this search that can we really find ultimate constituents, this has gone in a rather spiral fashion. Quite often, scientists claim to find a basic block. For example, during the Dalton days or before 1900, somehow when people started accepting the idea of atom, they thought, okay, 108 or 112 kind of atoms are sufficient to to, to play the game. However, this number is still very large, and when we study Rutherford scattering experiment, we find that the individual atom of chemist is no more divisible. It can be thought of as composed of a core nuclei where the whole mass of the atom lies, and around that nuclei we have electrons moving around or in the form of cloud, whatever you can think as permitted. So this game formally started around at the turn of the 1900, turn of the century, when we see Thomson giving us electron in his cathode ray experiments. It gave us his EY mass mass ratio. And of course, the Milken drop experiment gave us the charge of the electron. So these are the fundamental properties which are often required for every particle. We want to know what are the charges of this fundamental particle, what are the masses of the fundamental particle. And this question is not that simple as it apparently looks. When we go to the quark level, the question of mass is going to be more and more mysterious. Anyhow, Thomson model we all know didn't work very well. So Rutherford, when he performed alpha particle scattering, it reveals the point-like structure of the nuclei. So the whole atom seems to be almost empty, because if you look at the scales of nuclei and atom, there's a very large order, 10 to the power 5 order or so. So this way we find that the real mass is highly concentrated. So nuclear matter is extremely dense, and around that electrons are moving in a certain way. So the first picture was given by Bohr, that these electrons should move in those orbits called stationary orbits, which have uh, angular momentum as an integral multiple of Planck's constant. But we also know that the story is not complete, because we also need another set of quantum number like orbital angular momentum quantum number, magnetic quantum number, and also spin, to have a proper description of, of electron around this. I am deliberately talking about quantum numbers here because the use of quantum number is a typical feature of particle physics. We need quantum numbers to describe things. So we have various kind of quantum numbers which are familiar to us, which may not be familiar to us, and sometimes we are puzzled where we will end. Anyhow, but when this nucleus was probed further, it was initially thought to be made up of electron and proton, which is wrong. Everybody knows it's a class textbook material. In fact, Rutherford himself, I mean, suggested that there should be another kind of a particle, because it was easy to identify proton. It is nothing but nucleus of the hydrogen atom. So if you ionize the hydrogen atom, you have electrons, you have protons. But then, as you know, that there were problems in describing nucleus to be made up of only the electron and proton, which is a wrong picture, because obviously it's a small, long 11th class question that show that quantum theory does not permit, particularly the uncertainty principle, does not permit electron to live inside a region which is of the order of nuclear size. So we need a particle which is neutron, that is neutral particle, whose mass is very, very close to the mass of the proton. And his student Chadwick, around 1930, finally observed this neutron. So this nucleus, which is the core of the atom, is supposed to be made up of proton and neutron. Life looks really nice here, because what we need is only three kind of particles: proton, neutron to form the nuclei, and electron moving around it. So in this way, all those over 100 atoms can be understood as a combination of these three kind of particle. Overall atom is neutral, so the number of proton and number of electrons in a neutral atom should be equal, and the mass number, the difference of mass number, atomic number, can give you the number of neutrons. This elegant picture somehow around 1950, when lots of unstable matter was starting seen. In fact, that game started even in cosmic ray studies, because cosmic ray studies also showed the presence of new unstable kind of matter. So the more and more questions could be asked. Even the very question, how can so many protons live together inside such a small size of the nucleon, which is around one Fermi, or even slightly of that order. So obviously there is a repulsion. So there has to be new kind of force, which people call nuclear force. You can also call it strong force. So that force required a new kind of particle, which was proposed by Yukawa. He gave the meson exchange theory of strong force, and those mesons mass he also estimated around 140 MeV. MeV is the energy unit million electron volt. If you formula divided by c square, that will give you mass. Anyhow, but when we will see soon that hundreds of particles will seen, most of them are unstable, and you have to understand them. And whenever we have so many things, even at home, what do we do? When if we have a home where a large number of things are lying around, we start classifying them. We put them in certain sets, certain groups, and then try to see if there are some kind of actual connection between them. So those kind of approaches, which were done formally with the help of symmetries, internal symmetries, led us to the quark structure of protons, neutrons, and pions, and many such baryons and mesons. So these proton and neutron, they are the lightest baryons in the baryon family, and pion is the lightest member of the meson family. There are a large number of baryons and meson we will see soon. So people like Zweig and Gell-Mann, they worked very hard and thought that these baryons and mesons, which are several hundreds of them, cannot be fundamental, and there must be another layer of onion. And they suggested quark structure of hadron. Quark is just a fancy name. So in that way, we find that okay, in those days, that is 1962, three quarks were sufficient to play the game, but now we will have formally six. So six quarks, and they also appear in three different colors, and six lepton is the present picture of ultimate constituent at the present energy scales. You never know whether this is the end of the story or it may reveal another layer of onion. In fact, already in 1985, Harari, Israeli physicist, has proposed another uh, constituents which may be forming quarks and lepton. After that, many more scientists have proposed their model. Collectively, we call them preon models. But all those attempts are totally hypothetical because so far there is no experimental evidence, and we estimate that these quarks are leptons. If they have any size, it has to be much less than 10 to the power minus 16 centimeter. So this is the present picture, but don't take prions very seriously because they are not yet seen, and maybe they are there, maybe they are not there. So you can play with these ideas. It's an interesting thing. Pictorially, you can see the whole thing like this. You know, on the right hand side, I have given you crystal. In fact, in the very first sheet, I have basically shown this, that everything is made up of molecules, and I have also given their order of their size. Then molecules are made up of atoms. Atom is further made up of nucleus, nucleons. Nucleus is made up of nucleons, and these quarks and leptons are today fundamental particle. So this is the present picture, but still the question is there: if quarks and leptons, which we will learn more, are the ultimate constituent of matter. Of course, both these families have spin half h, so they are essentially fermions. And those fermions, how do they talk to each other? So how do quarks talk to quarks? How do leptons talk to leptons? How do quarks talks to leptons? And vice versa. So those questions will take us to formal understanding of forces. So now we know that there are only four fundamental interactions. So all transformation in matter, wherever they are occurring only as a consequence of these four fundamental forces. This is electromagnetic, strong, weak, and the gravity. We have already seen how electromagnetic forces take place. They bind atoms, they bind molecules, they give you everything around us, even your friction and all kind of forces which are seen, even your muscular force. So ultimately, the whole life is manifestation of electromagnetic forces. So that's the beauty of them. This is almost ever all encompassing forces. So everywhere we find electromagnetic is playing very important role, whether it is geophysics or condensed matter physics. So final picture of electromagnetic force which we will see is it is it is happening due to exchange of photon, and one and only one photon is required, which is massless. So this picture of which we technically call quantum electrodynamics started with Dirac's idea of quantization of field given in 1928, and there were serious problems of infinities. And don't please conclude that infinities appear only in quantum theory. In fact, infinities of this kind also appear in classical electrodynamics, but I'm surprised most of the time we don't talk about it. We should, because we will learn more that infinities in quantum theories are gentle than the infinities in classical physics. But I will talk about that some other time. So in order to tackle those infinities, we need special techniques called technically renormalization, which was formally developed by Feynman, Schwenger, Tomonaga in 1948. And these are three people who are working independently, and it is Dyson who make their work understandable to us. And finally, a picture was evolved. In fact, this idea of exchange, as I mentioned yesterday also, was originally suggested Faraday himself, because when when Faraday was questioned that how this action at a distance is taking place. We know that charged particle affect other charged particle at a distance. Sun control the motion of Earth, Earth control the motion of Moon at a distance. So how these forces are actually taking place. Faraday himself suggested the idea of electromagnetic field, but in his notes, he writes that though I have given the idea of field, which is of course understandable, appreciable, but I personally think exchange of something is going on between these two distant objects that is responsible for manifestation of force. However, time is too early to talk about these things. So that shows Faraday was a real genius. But the point is, are the two pictures really different? That is what we will learn in quantum description. We start quantum theory with wave particle duality. And when we perform quantization of field, we cannot keep electrons and electromagnetic field on different path. So if we are quantizing electromagnetic field, giving us the quanta photon, we also have to do similar thing with the with the electron. So the basic wave particle duality with which we start has to be properly generalized or replaced by another and more fundamental duality principle, that is the field particle. So in my lecture on forces, I will talk about those things in more detail, but in between probably we will also learn how the development of quantum mechanics is very important to understand these ideas fully. Anyhow, with this idea of electromagnetic, a brief, very brief idea of electromagnetic force, we can go to this strong force, which is responsible for binding of protons and neutrons. But we have to be a bit careful about the strong force, because strong force work at different level. Whether these two levels are different, isolatedly different, or they have some link, is one of the important question of today. So let me first talk about strong forces acting at the proton and neutron level. Later on, we will see the same force is also responsible to bring quarks together to give rise to the proton and neutron and many such particles. So at the nucleon level, you know that Yukawa proposed in 1935, kind of exchange of mesons is required to perform them. And as we will learn now, and probably you might be already knowing, that nucleons carry isospin. So isospin is acting like strong charge, and like charge is surrounded by electromagnetic field. In quantum field theory, we replace the field by virtual cloud of photons. In the same way, every nucleon is surrounded by virtual virtual cloud of ions, and these ions are exchanged among different nucleons within the nucleus. So that is how we need. And this number three is technically required from group theoretical basis also. But otherwise too, if you have two kind of particle, that is proton and neutron, you can easily see that we need minimum three kind of ions, that is pi plus, pi zero, pi minus. So if you want to use the language of isospin, you can call it isovector or isotriplet. So they carry isospin 1, whereas proton and neutrons carry isospin half. And we need to have these bands to be massive. Why? Because strong forces have a short range. Their range is of the order of 10 to the minus 16 meter, of the order of a Fermi. So it is a small exercise. If you have not done it before, you can do it now. Exploiting the time energy uncertainty principle, you can find a relation between the range of the force and mass of the ion, and of course Planck's constant c will speed of light will will enter into the formula. So from this simple formula, which is r equal to h over mc, you could guess what should be the mass of the ion, and that comes out to be around 140 MeV, which is all right, corresponding to the range of the order of one, one Fermi. But the point is, if this idea is so nice, why can't we apply it to all kind of nuclear physics and nuclear phenomena? We do have ion exchange, but do we have a proper understanding of ion exchange theory of strong forces? Answer is big no. Why? The reason is strong coupling constant of strong interaction is of the order of 13, which is 1,000 times larger than the corresponding fine structure coupling of the electromagnetic force. I hope everybody knows here alpha, the typical number, which is one of the 1 over 137, that controls the strength of the electromagnetic force. It is nothing but charge of the electron square divided by Planck's constant and speed of the light. So E square over H cross C, you can also take it as a small exercise. You know the charge value, you know the Planck's constant value, you know the C value, I mean speed of light. So put those values together and play with it. See if you can get a number 1 over 137. This is a little clue here which I can give you, that it's not that simple. You have to be careful about the units. Whether you are working in SI units or you are working in electrostatic units, so take care of the units and show that fine structure constant E square over HC comes out to be 1 over 137. Why this fine structure constant is so important? Interestingly, it is dimensionless, because choice of units always lie with the person who are actually working. We have been seeing large, if you go to since old times, we have different uh, units of length, mass, and time. But ultimately, we all know that SI we take to be the standard. So, but since everything depends upon choice of units, we need to find out something which is dimensionless. So E square over HC comes out to be dimensionless. So this is a nice number, 1 over 137, which controls the strength of the electromagnetic. So correspondingly, dimensionless scale for strong interaction comes out to be G square over HC, where G is the nucleon pion coupling strength. So that number is around 13. And all of you who have used perturbation theory know that if interaction strength becomes greater than 1, perturbation theory cannot simply be employed. This is one of the fundamental reasons that even today we do not understand physics of the nuclei. We have to be very, very careful. So what do? We develop models. We have liquid raw model, we have shell model, we have collective models, we have interacting boson models. So just model, because we don't have the theory. So even though we have idea that pions, and one more thing, who says that only pions can be exchanged? I can convince you, if pions were the only particle were exchanged there between nucleon, then the nucleus should have been stringed to point like thing. So what gives shape to the nucleus is exchange of even heavier particles called vector motion. Rho plus, rho zero, rho minus, they carry spin 1. Pions carry spin 0. Remember, don't confuse spin with isospin. Pions are spin 0 particles, scalar particle, but carrying isospin 1. There are three uh, members of that multiplet. In the same way, rho plus, rho zero, rho minus, they also form isospin 1 multiplet. That is three member, but they have boundary spin to be 1. They are the vector particle. And I can give you a general principle. Whenever you exchange spin 0 or spin 2 particle, force is always attractive. It is only the exchange of spin 1 particle which generate a repulsion also. So if there were only the pion exchange theory, then the whole nucleus should have been collapsed to point like under the attraction of the force produced by pion. So the stability comes when at very short range rho vectors are also exchanged. So you see that way that nuclear forces are becoming massive. However, this is only a high level thing. We have to go inside the proton. When we go inside the proton, we find that the quarks are there. So the nuclear force should also have a interpretation through the actually at the quark level. At quark level, strong forces occur as an exchange of 8 gluons. So this is what we learned from Gross, Wilczek, and other people who got Nobel Prize for that. Around 1972, they, they gave us quantum chromodynamics, which is the present theory of strong interaction. But does it mean it has solved all the problem? Obviously, no. So I will take this issue, of course, in more detail at appropriate time when I will be talking about forces. So still there is a question that can we derive nuclear forces through quark gluon kind of forces? This I'm especially giving to our young ones because they may be looking for new kind of problems. These problems have to be faced. But all of us know now about the third force because when first time nuclear beta decay was observed, people were a little puzzled how to understand this decay. So we call it technically a process occurring through the weak force. It is a mysterious force which people did not know at the beginning how it is doing it. What is happening is I will talk about these things in much more detail. But this is a very important force in high energy physics because we will see large number of particles which are unstable decay through strong and electromagnetic forces, but many low-lying heavy particles, unstable particles, preferably, they have only chance of decaying through weak force. In fact, there is a typical feature of weak force that they change the nature of the particle. Even if you consider nuclear forces, we call Rutherford a modern alchemist because by appropriate nuclear reaction, you can convert oxygen into nitrogen or the vice versa, or one element over the another. But the real transformation of particle occurs only through exchange, uh, only through weak, weak force. And that force is manifested through exchange of three particles which are known today, W plus, W minus, Z0. So these are called weak bosons. They are really heavy, very heavy. Iron was to carry mass around 140. Their mass is around 90 GeV. So their mass is 90 times higher than the mass of the proton. And the range of force is obviously slow because the same formula will work here also. So if you write R equal to H over MWC and take mass to within 90 GeV, again as a homework, you can see it and find out that range is 10 to the power minus 19 meter. Am I right here? I have to check my thing. Yeah, it is 10 to the power minus 18
Yes.
meter. Yeah. So the first theory of weak interaction was developed by Fermi around 1934. He took this idea of Pauli, who actually suggested that neutrino should be there in order to save conservation law in a beta decay active process. Uh, then this idea was taken seriously by Fermi, and he developed the first Fermi theory of weak force around 1934, which was formally put in the framework of quantum field theory by the great work of Glashow, Salam, Weinberg around 1965. So, with this pioneering effort of these people, they not only described weak force as a quantum field theory, but they also unified weak force with the electromagnetic force. So that is why Glashow-Weinberg-Salam theory is called electro-weak theory, because it synthesized, it unified electromagnetic force with, with weak force. So this theme of unification is very important to us, and it is actually continuing. So we will learn quite late among this series of lecture around 1985 or so. People even tried their best to unify strong electromagnetic and weak forces through together. Those are technically called non-unified theories. However, so far we have hopes. We believe in it to be true, but we have no experimental evidence for the grand unified theories, that is the unified theory of all these three forces, strong, electromagnetic, and weak. However, I'm avoiding talking about gravity for one reason, and actually for many reasons. Though gravity is very important to bind, for example, solar systems, to bind stars to form galaxies. In fact, only after general theory of relativity was given by Einstein in 1915, we first time could dare to develop cosmological model to study origin and structure of the universe. So it is very attractive, very powerful, very challenging. Unfortunately, we have its understanding only at the classical level. Whereas we have quantum field theories to describe strong forces, electromagnetic forces, weak forces, we still do not have any quantum theory of gravity, though very important people, great people are working to develop quantum gravity, but so far, to the best of my knowledge, it is not there. Somehow people want to have a quantum framework, though some of the predictions of Einstein, including existence of gravitational wave, have been confirmed, but waves can also be there in a classical picture. For example, Maxwell equation, in the absence of source, predict the existence of electromagnetic wave. In the same way, general theory of relativity, which is classical, does predict existence of gravitational waves, and which have been confirmed few years back. However, suppose someday we will be able to develop a quantum theory of gravity. In that case, again, field particle duality will come, and corresponding to gravitational field or space-time curvature, we can think of a quanta associated with the gravity. Because see, remind yourself, electromagnetic interaction take place through exchange of one photon, which is spin one. Strong force ultimately boils down to part level, which interact with each other through exchange of eight gluons. Why do we need eight? We will see later. Similarly, the weak force, we have a quantum field theory of weak force, which require exchange of three quanta, W plus, W minus, and Z zero. So in that way, one photon, eight gluons, and three W boson and Z boson, they all have spin one. But in gravity, if there is has to be a particle corresponding to quanta of, this field, it has to be spin two. So it is again a hypothetical particle. People who believe, who want to develop the quantum theory of gravity, they believe in it. But this graviton, if it is there, it must have spin two. The reason is very, very simple, because gravity is always attractive. You can call it also force of love, because it always accept, never, it can never repel. So this is the picture. I hope it is clear, because this sheet I added today in a hurry. I hope everybody can see it. Is it clear, the Shastriji? Hello?
Sir, not very clear.
But I think I can explain it
Hmm.
largely for me. See, in this way, I am giving you a picture of all kind of elementary particles which we have seen. Okay? Obviously, list cannot be given, but I am giving you family wise. So, and because particularly I have added this sheet, because I'm not very happy with the books which are giving a classification of elementary particle. Classification of elementary particle can be done in a number of ways. This is to best of my satisfaction. That elementary particle, first of all, can be categorized in two broad categories. That is matter particle and quanta of the forces, which we have already introduced. So let me first talk about the matter particle. Matter particles are divided in two families, which are called hadron and leptons. So leptons form their own family, and there are only 6 leptons, electron, muon on top. We will learn more about that. And they seem to be fundamental particles today. However, all the hadrons, where are several hundred hadrons have been seen in collision experiments and in, of course, cosmic rays, etc. But they are again divided in two families, that is called mesons and baryons. In some books, I'm not against that. People also add antibaryons. So we have mesons, we have baryons, we can have also antibaryon. Antibaryon have one-to-one correspondence with the baryon family. For example, in the baryon family, I have put in proton, neutron, sigma plus, sigma zero, sigma minus, lambda. This is so many particles. So all of them also have an antiparticle. Proton has corresponding antiparticle, antiproton. Neutron also has its partner and antineutron, and they have been seen. And in meson family, they carry baryon number 0. Again, I'm now introducing a new kind of quantum number. You can, for example, mass number in nuclear physics is nothing but baryon number. You are just counting the number of proton and neutron inside the nucleus. So mass number is formally called baryon number in the subject of high energy physics. So mesons carry baryon number 0, baryons carry baryon number 1, antibaryons carry baryon number -1. So you see that how new kind of quantum numbers are they have started appearing here. So we have mesons like pi mesons. I have talked about that. We have heard about proton and neutron. And as I mentioned in lab experiment, high energy experiments, new kind of particles have been created. So we have to list them. So there is a large group of several hundreds of mesons and baryons. So obviously they are not fundamental. One more reason is they have size. In contrast to leptons, these baryons and mesons have size of the order of a Fermi or so. So this sized object is most likely not going to be fundamental. And another hint which you can get right away from the nuclear physics is proton has magnetic moment because it has a charge. Quite understandably. Neutron is a neutral particle. How can it have active magnetic moment? So in fact, proton also has anomalous magnetic moment besides the expected moment on the basis of spin-half description. So it means that this anomalous magnetic moment might be coming because of some internal structure of the baryons or these nucleons. So ultimately, several hundreds of these mesons and baryons are supposed to be made up of so-called another layer of the another layer of the onion, quarks. And for we need till today 6 kind of quarks. The name is up, down, charm, strange, top, bottom. Not only that, we have six quarks which are called quark, quark, quark flavors. But each of these six quark appear in three different colors: red, blue, and green. And please do not confuse this red, blue, and green color has nothing to do with ordinary color which we see around. Somehow, in particle physics, we are in the habit of using these fancy words probably to attract students to do research. So in that way, quarks and leptons are supposed to be the fundamental particle, ultimate consciousness today, and both of this family interact through strong electromagnetic, weak, and of course gravity is always universal. So in order to these forces to occur, we need photon as quantum of electromagnetic field, gluon as quanta of strong electromagnetic field, and W plus, W minus, and Z0, three quantas for weak electromagnetic field. When I say weak electromagnetic field, I do not mean combined form of weak and electromagnetic field. It is like electromagnetic field. We have weak electric field, we have weak, weak, weak magnetic field. All those things I will talk about in more detail when I will focus on, on these forces. But besides all this particle, we also need one typical particle, at least one of them, and that is called Higgs boson. It is a spin zero boson, and everybody must have heard few years back the story of God's particle. So Higgs boson is called God's particle. I will talk about that later on. In fact, one complete talk can be given on the discovery of Higgs boson. It's very heavy particle, and this particle is responsible to give the mass. Sometimes I often ask students, we use various terms like space, like time, like mass, like charge, as if we really understand them. To the best of my knowledge, we have a huge amount of information and actually literature about these fundamental things, but we still do not understand that. So that is why query can be extended. I hope everybody has now seen these families.
So this is a good time to stop.
We can do that. Sure.
Yeah.
Good
I
night.
think
Okay. It's already, I think, 4:52. Fine.
Lalit, you can pause the recording here.
Yeah.